All right, good morning. We're going to start looking at CT imaging this morning. And at the end of the class, we're going to also discuss some times for extra sessions for linear systems for those people who want to do a little bit extra work and catch up for linear systems. And Dr. Liu, I think, has some additional material that we can look at. So don't let me forget about that. Some of the figures in today's lecture will come from a textbook that's Bushberg et al. There's 4 authors, The Essential Physics of Medical Imaging, Chapter 10. And I can probably put Chapter 10 in the module for this week so that you have the associated text for these figures. But a lot of it comes out of prints and links. So we're going to look at the hardware and just the methodology of collecting data to create computed tomography images. This is from the first lecture where this is a standard CT scanner here. It's basically a cylinder, and the patient is on a table. That table can move with precision in this direction, the superior-inferior direction, or the Z direction. And the precision of those motions is fairly high, sort of 1/10 of a millimeter, something like that. And nowadays, these tables move quite fast. This patient is getting ECG leads attached so that the data acquisition will be gated to the heart. And when you're looking at the raw data, you will know at what phase of the heart cycle you're in when you're looking at that data. And there's also, although this isn't connected to the patient at this point, lines would come out of this contrast injector into a vein, usually a decubital vein here in your arm, and contrast would be injected at the right time, or you would inject the contrast and then image the patient at the correct time. So state-of-the-art CT images are pretty outstanding. These are sort of recent images of a human brain with CT. You can see you have imaging the brain with X-rays is a little difficult because you have a bony skull around the entire brain, and so to get X-rays through the skull is kind of difficult. And it was a major challenge in X-ray radiography for years and years. But you can see very nice soft tissue contrast now with CT. This is an image that is a maximum intensity projection of vessels. And so when you inject contrast into the bloodstream and then image the brain, you can appreciate all of these small vessels perfusing the brain. So if you're looking for something like an aneurysm, like a large distension of the vein, or some area where there's a blockage and downstream of that blockage is blocked off, it's a really good imaging modality. It gives you very high resolution 3D imaging data. You can get very rapidly now images of the entire body, like from head to toe, essentially, on a CT scanner. And you just push the patient through the scanner and continuously acquire data, right? And so in this case, we're going from this patient's collarbone all the way down to the bottom of their pelvis in order to measure the function or the shape of their aorta. The aorta here has a distension here, and it's being highlighted by a contrast agent again, which is in the blood, showing this. Now, this patient was just essentially pushed through the CT scanner, at about a meter per second or something like that, as they're being scanned, and the whole thing's done very rapidly. So each, this is cut into slices. Each one of these slices, axial slices from this, is like 512 by 512. And then you can have many thousands of slices, like up to 2,000, 4,000 slices of data to go through, right? So it's a big data, problem in its own right, even though when you look at it like this, it's just a picture. It's a single picture, right? There are interesting artifacts in CT which people are still combating. For example, if you're imaging through a patient's hips and they have artificial hips, and so they're metallic objects, they attenuate X-rays very highly. And so in the views that are taken through here, it looks like there is nothing in there because inside here, because you just can't see in there, right? And so the reconstruction is full of this metal artifact, but smart modern techniques for image reconstruction that use modeling can get rid of that artifact. Here's an example of CT volume of the human heart. And again, it has contrast in it. And so this is the left ventricle. You can see with the left ventricular blood here, right ventricles over here, the coronary arteries. One is here, one is here. Atrium, left atrium, aorta. This is the descending aorta. And with a 3D image analysis program, in this case, this one's called Osirix or Horos. It's free. You can load that volume data in and image or probe that data from multiple directions. So it's essentially isotropic 3D data, so you can look at any given slice through the patient retrospectively. Here's an example of rendering that volume data as essentially an object that's opaque, and you have a lighting model, and then the vessels show up as these opaque objects here. This type of data is not commonly used for diagnosis, but it is used to determine whether or not the images look reasonably good. When this data looks good, you know your images are probably artifact-free, and so clinicians then use the raw images themselves in stacks to make the diagnosis. Another way of visualizing this type of data, where you have a object that is, coursing through three-dimensional space, is to do a projection of that object onto a single plane. And so now this vessel is running through 3 space, and what we ask is, we take a slab and we look down through the slab and say, what's the maximum pixel inside that slab? And so it's like taking a projection image, and then you get to see the contiguous structure of the vessel. It's very helpful in determining whether or not there's a lesion there. This is the left anterior descending coronary artery. This is the right coronary artery, and you can see, you don't have to be a rocket scientist or even a trained radiologist to look at that and say, well, that vessel looks pretty normal, right? It's just a nice uniform shape. It's wide open. It's normal, right? And coronary CT has a 99.5% negative predictive value. So that means when you call somebody normal, they are normal. It's very hard to make a normal-looking picture if you're not normal, right? Vice versa, it's different, is that there are a number of ways in which you can make a picture look abnormal when the person is in fact normal, but the reverse is not true. This is CT data that's taken dynamically. You can take it continuously in time, and then you reconstruct images, say at 100 millisecond intervals, and then you play those images back just as a movie, and there you've got a beating heart on your screen. And this is something that isn't widely appreciated even to this day in cardiology departments. When you show this type of data to either cardiac surgeons or cardiologists in an open convention, that they're there for some other reason, and you say, oh, this is what your CT scanner can do, half the mouths in the room, their jaws just drop open and say, they what? Which is fantastic in that, medicine is so firmly entrenched in its practice that just discovering something new is quite hard for physicians. It's remarkable. So this has been around for about, I would say, 5 years or something, and still it isn't widely even known to a lot of clinicians that you can do imaging like this. So this is CT data. You can do image like that with MR. Okay, so let's look at how that data is collected, and we're going to go through progressively more complex machinery, basically to collect the same data, just more quickly. Okay, So the initial computerized tomography proposal or system was built by Godfrey Hounsfield, and he worked for EMI, and we talked about that in the introduction. And EMI had a lot of money because the Beatles had just, made a lot of money. And so they had this big research program, and they let him, he worked on business computers, and then wanted to do a sabbatical on something crazy, so he did this imaging project. And he thought if he had a radiation source here and a detector down here, if he rastered that across the patient or across an object and measured the projection, like the attenuation of the X-rays as he rastered across, and then rotated it and did it again and rotated it and did it again, then he would be able to make a two-dimensional picture, cross-sectional image of this thing, right? And this is his original experimental device that he built at EMI with used parts around the lab. This is actually not an X-ray source. Inside this can is a radioactive substance that is just shooting out gamma rays and X-rays and all sorts of radiation. But he put a pinhole right here so that radiation was shooting out a hole right along here. And then this is a sodium iodide crystal that you use for nuclear physics experiments. Like when a high energy photon hits it, you get a flash. And then he counted the clicks as it came through here. And so essentially it's like a SPECT scanner in a way, right? It's a nuclear source and it goes through here, but it's a fine beam because he focused the beam down. So what he did was this tray of material rastered across the beam, and then he rotated the tray and then rastered it back and rotated the tray and rastered it back. And it took about 2 hours to collect everything because the amount of radiation coming out of here wasn't very high. So you had to pause and collect data for a little while. You can make this faster, obviously, by making the beam of radiation a little bit broader. You can make it faster by making, instead of a very small, sort of non-powerful source of radiation, you can put it in an X-ray tube there, an X-ray light bulb, make it powerful. So you've got a lot more radiation, and that way you can raster across more quickly, right? And so this was the next generation of this product, and this is Hounsfield again. They built this thing at EMI with this type of design, where the X-ray tube and this linear detector rastered across the patient. It rotated and it rastered again. And it was actually done only in head scanners originally. And then the next development, or next generation, is if we have a powerful enough source and enough X-rays, put it far enough back such that the beam, the fan beam, illuminates the entire field of view, and then put enough detectors behind such you get it all in one shot. So you don't have to raster, right? Now, it's slightly different, right? Because at this point, the beams, if I'm looking at this detector, it's something at an angle. So I'm not doing consecutive straight line shots through the patient anymore. So we're going to have to take that into account. And this is called fan beam reconstruction, and it's a pretty simple modification of just the reconstruction that occurs when you do straight line beams through the patient. So now we have about 1,000 simultaneous beams in one shot. If we have enough X-ray power, right, we can get 1,000 of those. And rotate to a new angle, take another shot, get another 1,000 projections through the patient. Nowadays, you take about 500 to 1,000 of these angles, bing, 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 around the patient. And one of the things we'll figure out is how many angles do you have to take, to get a decent picture, right? It's more than 8, less than 1 million, somewhere in there, somewhere in between, right? So we'll figure that out. And this is called the third generation CT scanner, and the CT scanners basically stayed like this, right? Small modifications will occur next, but the other modification that occurs is once you have this geometry of a fan beam illuminating the whole field of view and 1,000 detectors down here, Well, what's the next way to make things twice as fast, right? We'll just, or 4 times as fast, we'll just put 4 detectors like this. And we'll do 4 slices simultaneously, right? As opposed to doing 1 slice, shifting the patient, doing the next slice, shifting a patient, doing the next slice. Let's do 4 slices simultaneously. And so in the superior to inferior direction, scanners over the mid-90s through 2000 through now have just made more and more slices in this direction. Until now we're up to, Canon has a product that has 320 slices in this direction, right? And GE has 256. Philips has 128, I think, and Siemens has 128 in this direction. And so it's orders of magnitude more data than the single slice scanner of the 80s. Take note of these coordinate systems because they'll come up. When a patient is lying down like this and you look at the image, the coordinates that should be in your head are superior to inferior, so the top of their head to their tip of their feet, anterior to posterior. If we had a dorsal fin, it would be on our posterior side, right? We don't. And then left and right. Okay, and so that forms the 3 space. So when you're looking at data in 3D, usually what's labeled in the corners of the image or the sides of the image are these coordinates, right? Usually just the first letter. So here's a picture from that Bushberg text that I told you about of detectors in the plane, about 1,000 of them, across the fan angle. This is usually about 40 to 50 degrees, this fan angle. And then you have a cone angle, depending on how many detectors you have in this direction. In the early days, and this is still done with wide-angle detectors, one mode of CT acquisition over a larger field of view in the superior-inferior direction, the Z direction, is to do step and shoot. So here's the configuration. The patient's in the scanner. And essentially, to get multiple volumes through the patient, we'll take one volume and then move the patient, take the next volume, move the patient, take the next volume. So the patient is stationary while the gantry is turning, and then you get a fixed volume at that location. And that's called step and shoot. Another common way of acquiring data over a larger volume in the Z direction or anterior or superior to inferior is called spiral or helical scan. The reason it's called helical scan is you continuously rotate the source and the detector while continuously moving the patient, and therefore you essentially, if you look at the source, you get a helix through the patient, right, as to where that source has painted. If you had a beam and it was marking the surface of the patient, it would form a helix. And in order to get any arbitrary location in the 3D volume, you have to interpolate between helices on either side of your point, unless you're sitting right on the point, right? And so that interpolation is done to create a 3D volume data set. Step and shoot makes sense when you have a wide detector in Z. They have 256 slices. It makes sense just to get all 256 with a stationary patient and then move the patient, get another 256, right? In fact, when most scanners go to helical mode, they narrow, even though they might have 256 slices on their detector, they narrow it down so that you're working in the central volume of that detector. That's because the distortions of things towards the edge of that cone start to make it quite difficult to do the interpolation. So here's the movie. I think I showed this at the introduction, but it's a nice graphic of how the detector and source rotate. It makes a bit of a noise, you know, and now that the rotations are at kind of a high frequency, the noise is sometimes a little alarming, so they've been trying to make these things rotate very quietly. So here's the detector in Z, 1000 this way, 256 this way. You can, using a shutter system at the top of the source, you can narrow down your field of view to a smaller than the full 160 millimeter field of view. And there's the voltage source and the X-ray tube itself. That's what it looks like being installed. This was ours. We got this delivered about 2.5, 3 years ago, something like that. And so here's the gear. It's just like watching the techs put this together. The field engineers put it together. It's just like IKEA on steroids, right? I mean, they have these huge volume books, and they have to like bring out these parts and clamp them together to within certain tolerances and things like that. So it's actually amazing that they can mass produce these things and have them installed and they all work, because the mechanics of this thing is pretty impressive. So I've put here for you a couple of video links. We just looked at this one, but you can look at, this is always fun. You know, engineers eventually in some hospital take the covers off a scanner and just run it as fast as they can and videotape it so you can see the guts of the scanner moving. And so that's what this guy is here. It's pretty entertaining. So another take on this is like, if we have, so what Siemens did is they said, okay, we'll make a detector that's in Z, we'll make it, say, 128, or maybe it's even 64 in Z. But we have a regular CT scanner, so I have an X-ray source here and my detector here. And you look at it and you go, oh, there's some space left over. I'll put another X-ray source here and another detector here. So now you've got one detector here and one detector at 90 degrees. And so you're basically simultaneously doing these orthogonal shots, which should, just increase the number of angles you're getting for each rotation, right? So you basically can get a CT scan in half a rotation because you've got these extra detectors. So it speeds up the process of getting all of the data you need in the theta direction, in the rotation direction. The other thing you can do is you can make two different pictures. You can make X-rays of a different energy. Say this is 70 kV, this is 140 kV, so you get two separate pictures. And they're X-rays of the same object, but taken with different energy X-rays. I've put on here a link. You can just watch this thing rotate. It's pretty impressive to see that thing go. And this is a movie off the Siemens website. And it's to scale. That's how fast the dang thing works. That's how fast you can image a person on this thing, right? This is normal speed, not called turbo, but that first one was their turbo mode. And so the table moves like twice as fast as a normal table, right? Because they can get all their data in like half the rotation, right? And so the roof, I've been in it, I've been scanned in it, and you sort of fly through it. And I really don't know about the acceleration. Like you'd think that when you're zooming through there, like your organs would be sort of like, because they're being accelerated, right? They claim, no, we have the ramp up, acceleration and velocity such that we hit our steady velocity when we're imaging, but I don't know about that. I would love to try, like, put a bowl of water on one of these tables or something, just to image it going through and see, like, was it like tilted up to one side or, Anyway, this turbo flash mode is pretty impressive. So this is the history of CT scanning from the early 80s. Remember, Hounsfield did it in 72 over here, right? And then by the end of the 70s and the early 80s, we had clinical machines that were pretty widely available. but you can see the usage was in the low millions of scans a year. And then over the decades, and this is only going up to 2008 or something, 2007, you can see the number of CT scans done in the United States, right, is getting upwards of close to 100 million. It's over 100 million now. Right? Just think about that number just for a second. 100 million. How many people are in the United States? There's 300 million people in the United States, so it's like 1 in 3. That's not how it works out, but that's how many scans are being done. Right? This is like an extraordinarily useful tool, and it gets used a lot. So when people show up at the ER and they have pain that in their chest and nobody knows what it is, you put them in a CT scanner, just like that, right? See what's going on in there, right? And from my perspective, it's a fantastic thing to do. I want to know what's going on, right? You know, or if the person's having a stroke or whatever. However, once you get up to like 150 million scans a year, that's a significant source of radiation to the population, right? Now, we're talking population dynamics now, not individual dynamics. So a number of people have looked at this and said, well, should we think about it, you know, about putting this much radiation into the entire population? But you can see the growth has a couple of knees in the curve, and the first was helical. And remember, during this period, you had to rotate through a set of angles, stop, and let the cables unwind, rotate back, right? And so that, you could only do it so fast. An exam would take 25 minutes for a single patient or a half an hour. Helical CT was introduced by Siemens once they had these brushes that they could get both power and digital signals across from the gantry, and when it was in continuous motion, right? And so you just start it moving, and then you can do all your CT, and then that obviously made scans much easier, and they were much faster. The image quality was much higher, and so that was a jump. And then we started seeing 2-slice scanners, 4-slice, 8-slice, 16-slice, 32-slice. Then it got to 64-slice. And this 64-slice VCT scanner by General Electric was the best-selling medical imaging technology ever, right? 64-slice CT scanner, because it's just so darn good, right? To have one of these at the front of your hospital, you know, and in radiology, patients go through this thing. You just know what's going on by the time they get out of that scanner, right? Because there's not motion artifact, all this stuff. So it's a great product. And everybody followed suit. Like every vendor went to these larger slices. And so the number of scans just became fairly large. So this is a table out of Prince and Links, and it you know, describes the parameters and of the different generations of CT scanners. You will not be responsible to know this history, okay? You know, for those of us who were alive during this entire history, this table is quite interesting, right? For you guys, I mean, you're born somewhere in here, so it doesn't matter, right? What happened back here? It's like this stuff's, it's historical artifacts, but it's nice to know how, you know, the steps. The other thing that's nice to know is like the first CT scans took, you know, half an hour to make. And so you had to believe in the technology. You know what I mean? An X-ray, you stand somebody in front of an X-ray film to take a diagnostic X-ray shot, and it takes milliseconds, right? And now you say, I have this technology that will take 1/2 hour per patient, will give them 500 times the dose of an X-ray image, and you know it will cost maybe 15 times that. You say, okay, would you invest in that technology? So you have to have front-end believers when it doesn't look great, right? To get it to this point where it just crushes everything else. Right? So here's a modern detector. We looked at this briefly before. This is the superior to inferior direction, or the Z direction. Each one of these is in that 256 simultaneous slice acquisition, right? So the X-rays are coming from up here and hitting this detector here. You can look at details of this thing on this really nice video that it sort of explodes it and brings things out and puts them back and stuff like that, so you get to see its scale. This is a very important part of any X-ray imaging detector, and it's the anti-scatter grid. And so you can imagine, well, you know what light, when you have a flashlight and you put it on your finger and you look at the light that comes through, it's just a glowing red sort of, uniform signal, right? And that's because the light is just bouncing off everything. It's it never just goes straight through. You don't really see an image of like photons that have gone straight through. Kind of the same thing with X-rays, except a lot of them go straight through, some of them don't, right? Some of them make that image that the flashlight does, and that it's just a fuzz because they're bouncing off things and hitting the detector from a different angle, right? And so that's called scatter. So if you have a photon coming in this direction and it's going to hit the detector here and give you and light it up, your system will think it came from up there. So you want to eliminate that photon. So ideally, it never makes it past this grid. It gets absorbed by the anti-scatter grid. And it's an important feature. And ideally, you have infinitely narrow cells that have fantastic attenuation of X-rays, right? That's what you would like. This is a video. There we go. Of what it looks like to look through an anti-scatter grid. So there's these dark objects on a backlight, and then you tip over, and then you can see that there's a primary image there, and then there's some, if you get off to an angle, it basically disappears, right? And so this, when you're looking through, you can see there are walls and cells, and you want just the X-ray coming through the cell cleanly, and if it's at an angle, it's going to hit a wall and get absorbed. So the basic diagram of how X-rays pass through a person and are detected on our hardware looks like this. We have the detectors along here, and we're going to read out, they make a flash of light when an X-ray hits it, and then that flash of light is turned into a voltage, right? And so we read out a voltage on each detector over a certain time and plot that, and it's proportional to X-ray intensity. Okay? The actual, there's some scaling and all, you have to do dynamic range adjustments and things like that, because some of the detectors will have an enormous signal and some will have a very low signal, and so there's a lot of encoding that goes on, but the basics are pretty simple. If we could measure just the signal coming out here, if it's linearly proportional to X-ray intensity, then if my source is up here and I pass through the patient, say right from that, anterior to posterior side, and I hit their sternum, or I could hit their spine, I have two possibilities of hitting bone on the way through there. There's a high probability that those X-rays are going to get absorbed, and you get a very low X-ray intensity measurement. For this angle, for this projection, and over these detectors there, we're going to see a low measurement. For this one, I'm going through soft tissue, then basically air, as long as basically air. It's maybe, 5% water or something like that. And then some more tissue. And so I will get a high intensity of X-rays at this detector, right? Because it's gone essentially through air. And then if I'm outside the person entirely, I will get, an intensity of air, which is just not attenuated by anything. Air doesn't really attenuate X-rays very well. Right? These measurements actually are kind of important. because what we're going to see is you really want to know what your baseline intensity from the tube is that is being shot at the patient. You want to make that measurement, and you can make it ahead of time with nothing in the scanner, right? Which they actually often do. They calibrate the scanner and see what the intensity would be if there's nothing there, because we're really interested in the ratio of this intensity to this intensity, right? You could try and calibrate it so that every time you clicked on MA and KV, you knew precisely what that intensity was, but that calibration won't last for very long, it turns out, right? And in fact, it may not even last for the whole turn of the gantry, because as the tube heats up, the flux of X-rays may change, right? So you basically have to have a dynamic estimate of the incident beam. So oftentimes the outside detectors are set to do that. So now we rotate our source to a new angle, and now the central detector is here. It's going through less bone, right? It might have hit a rib here or something, but it's not going through the sternum or the spine. The central detector is looking back at the source through mostly soft tissue, and so the central detector has a higher intensity of X-rays on its count. And then this guy over here is the one that was the lucky detector that's looking through that bone, right, this way. So you essentially just measure this at about 1,000 angles, okay? So I've got 1,000 of these functions, these profiles, and we're going to use that to reconstruct what's in there. This is what a modern Hounsfield experiment looks like. This is an X-ray tube. It has sort of a shutter here that can control the width of the beam and the energy of the beam by putting filters in it. This is a very sophisticated shutter here that will actually change the Fourier dynamics of the beam. This is a multiple aperture device, but this is very brand new technology. And then here's the thing you're imaging, and here's our X-ray detector. This is off-the-shelf, X-ray detector that you would use in a fluoroscopy system or something like that. And you just set it up so that it's orthogonal to your X-ray beam. And this is the phantom that you're going to image. And just like the Hounsfield experiment, what you do is you rotate the phantom, right? So you have absolute control of rotating that phantom. And you create the X-ray image that way. And so a lot of X-ray imaging laboratories across the country, they have setups like this. Right?
Can you
Yeah.
talk more about that?
Oh, this guy?
Yeah.
Well, basically it's taking a beam of a certain intensity as a function of space, and then instead of making that uniform intensity as a function of space, if you have some knowledge of the object and I need more X-rays over here than I do over here, it makes sense just to put more X-rays over there and not over here, right? And so it will modulate the X-ray beam to if you have some information about what it is you're imaging. For example, if you're imaging multiple frames of the same thing, right? When you're doing a contrast injection, or it's a patient who has been imaged before and is coming back for a follow-up image 2 weeks later, you should be able to actually image them with about 1/3 of the irradiation that you got the first time. Because there's a lot of stuff, you know what it is and you don't care what it is. So why even illuminate it? You have to know what it is in order to reconstruct the image correctly, but you don't really have to know what it is in great detail. And so this modifies the X-ray beam to adjust for that. But that's not on modern scanners yet. It's all still in laboratories right now. So this is essentially the increase in the pixels per unit time. You can think of it as image pixels per unit time or samples per unit time of a CT imaging experiment over, 19, Hounsfield's initial experiment to 2008. And it just follows Moore's law. It's not surprising, right? It's just like as you have electronics that can cope with more data, you build machines that give it more data. And so that's, when Hounsfield did it, they basically took all this data and fed it into a huge array processor to do an inversion of the whole thing. They didn't do convolution back projection or anything. So, and it took days to compute the first images. So the first clinical product, you got 2 80 by 80 images, and you got 2 of those every 20 minutes, right? So this is where you have to be a believer, right? Because that doesn't make sense. Financially, economically, all of the, VC parameters that you would put in front of a bunch of people investing in something would laugh at it, right? And just say, well, that's ridiculous. And they'd walk away. So this is why, the people who don't quit, just keep going. And now we're at 320 512 by 512 images, actually every 140 milliseconds. You only need a half turn, right? So it's pretty impressive growth. In order to do that, one of the things you need are X-rays in a short amount of time, right? So if you have, 5 minutes to image a patient, you don't need a huge burst of X-rays because you have 5 minutes to collect all these X-rays. If you're trying to collect all of this information in 140 milliseconds, you need a lot of X-rays in a short period of time. And so these are very bright X-ray sources, right? These are specialty X-ray tubes that make huge X-ray flashes, right? And as you can see, up to 2008, and we're going up here with this new generation of tubes, where you're looking at 100 kilowatts, right, of X-ray tubes. So, take 100, you know how hot a 100-watt bulb is, right? Everybody, I guess you do, yeah. So you're going to take a 100-watt bulb, now take 1,000 of them, right? And then put a big lens over top of you and turn them on. That's the kind of energy that's coming down here, right? And it's all done in a very short period of time. So it's a lot of power. And they're becoming more powerful because we want to image in shorter and shorter amounts of time. So going back to lecture 1 where we looked at X-ray physics, if you recall, the relative X-ray intensity that comes out of an X-ray tube as a function of photon energy looks something like this. This is the relative number versus photon energy. So if I set the voltage between the anode and the cathode in my X-ray tube at 100 kilovolts, right? I accelerate the electrons across the gap, and they hit the anode and produce a splash of X-rays. And in fact, coming straight out of the metal, the energy profile would go up to this axis here, right? The highest energy I could see would be 100, and then I get higher density of lower energy electrons because of that Compton effect, right? The Compton effect produces this whole spectrum of X-rays coming out. The only way I can get the 100 is if the electron goes in and comes right back. Now, what happens is as the X-rays exit the target material itself, the target material will absorb some of them, right? The lower X-rays, and the glass on the outside the vacuum tube will absorb some of them, and then you actually put a filter, a very thin film of copper or aluminum or something to also filter out lower energy X-rays so they don't hit the patient. So you wind up with something that looks like this. So it has a central peak, and when you're modeling X-ray imaging, oftentimes if you want to model a monoenergetic X-ray source, you would just take the mean of this peak, right? To say, okay, I can't really track X-rays at all of these energies, say for 100 kV. I'm just going to take the mean, which is here, which is like 50. And I'll do all my calculations there. Not a great assumption, actually, but reasonable for many purposes. Right? So the flux is integration of this function SE, which is the density over the energy spectrum. And then the intensity, so the intensity is like the amount of energy coming out in what would cause a flash in the target. You multiply by energy to get that, so it's this integral. Okay. Remember, attenuation had a simple function, simple process. If I have photons coming in with a certain intensity, and then the photons pass through some material, whether it be water or bone or metal or whatever, I get an intensity coming out, and this is my distance through that material. It just goes with this simple equation, the intensity in times an attenuation, right? This has to be between 1 and 0 is my intensity out. And this exponential decay characterizes the material. So this again, we looked at this diagram before. If I have X-rays hitting this material, 20% absorbed, 20% are absorbed, 20% are absorbed by the material, and you plot that, it fits very nicely a mono-exponential decay, where this is the characteristic of the material itself. If you want to derive it in the book, Dr. Prince et al., they derive it, this equation from sort of discussing it in first principles if you want. And it's a simple linear first order equation, just like if you had a hot cup of tea, right, and you put it down, the rate of change of the temperature of that cup of tea is proportional to the temperature, right? So when it's really hot, it cools down faster than when it's close to ambient temperature, it cools down slower. That's sort of the first equation that you run across in differential equations, right? And this is its solution. So, you'll see this equation in this form many different ways. And it comes out often as called Beer's law in X-ray attenuation. So the interesting thing happens when you have an inhomogeneous slab of material, right? So now a person isn't a bag of water or 1 millimeter of copper, right? They're this sort of conglomeration of stuff. If I draw a line through any beam through a person, I'm going to get different mu values as I go through. Bone, muscle, blood, contrast agent, etc. as I'm going through. So in order to get my final intensity, right, of the beam, that's if I hit the patient with an intensity I naught, and I look through that beam length through the patient, what I have to do is integrate the mu values along that path, right? And so the intensity at any depth x is proportional to the integral from where I start the attenuation to that depth x, over the length of the attenuation, right? And then, to be absolutely accurate, we also have to acknowledge the fact that the mu value, or the amount of attenuation, is energy dependent. And so high energy X-rays will not be attenuated as quickly as lower energy X-rays. And that's, if we go back to that first lecture, there's a graph and it shows you the mu values as a function of energy. So really we need to actually put into here mu of x, and we have to look at what is the spectrum of the X-rays that is hitting it. Perhaps, to think about it in simple terms, if we could divide our energy spectrum into 10 bands, very low energy, a little bit more, so that SE function is just 10 bands. I would just calculate 10 different images, right? And the mu value would be sort of the mean of each band, and then add all of those up to get my final image. And that's this integration over energy. That's a real pain in the neck, to say the least. And it's very hard to measure, it turns out, the energy spectrum of an X-ray tube in your scanner. You would think that would be something that's easy, right? But it turns out it's not that easy. And it changes, depending on your MA and things like that. And so to like completely map out that energy spectrum turns out to be a bit of an ordeal. So oftentimes when we're doing the math of CT, we're just going to assume we have monoenergetic X-rays, right? And make life a lot easier. And then you can just say, oh, if we do everything for monoenergetic X-rays, all I have to do it is 10 times, once for each one of those energies, and then add those up, and that'll give me my final image, right? So this is in a Prince book. Let's set up the coordinates for doing CT reconstruction. And this is straight out of their book. They have a function, right, which is going to turn out to be the linear attenuation coefficient as a function of position. And it's our patient. And the angle of the projection of the X-rays through that patient will be, let me get my laser on, will be parametrized by this angle here, theta. Okay, so if theta is 0, I'd be doing vertical beams through the patient. Here, theta is about 40 degrees. I'm doing beams at this angle. And then if this is my detector along here, I'm going to parameterize my position on the detector with another real variable L. Okay. So I can now parameterize each line through the patient with two parameters, L and theta. Okay. So this thing here, that line, is basically all of the XY values in the plane that satisfy this equation, right? And all of those XY values in the plane that satisfy this equation sit inside this line right here, right? And so it's just an implicit, equation for a line in the plane. If you really want to, you can make it into y equals mx plus b. If that's how you like lines in the plane, then you can just solve it, here. But that's how we're going to parameterize these lines, because that's how our detectors are laid out. Now, those of you who are thinking ahead or astute, you're saying, well, wait a minute, that only lays out parallel lines. And you showed us that we no longer have parallel lines. We have this fan beam thing, right? So we'll get to that. Okay. So the CT line integral, which we talked about, the intensity at any detector is the integration from the beginning of the X-ray beam to the detector, 0 to D, of the linear attenuation coefficient through space as we go along that line, right? And then we add up all of the energies. Right? So we do it across energies as well. We're going to do a monoenergetic approximation for all of these, essentially. So all this integral just gets reduced to making mu a value that is, just has one value in terms of energy. Okay? say E, the average of this thing here, the average energy, we'll just plug that in and use that. Right? Make life easier. So now we're going from the source to the detector integration along that line of the linear attenuation coefficient is going to give me the intensity of my measurement at the detector, right? Given that I start out with I naught. What we plot as our raw data is in fact the logarithm of the image intensity divided by what we started with. Okay, so if this is 1,000 and this is 500, it's a log of 1/2. So this number is always going to be between 0 and 1, right? The log between 0 and 1 is always negative, so we'll just put a negative here, and that gives us a positive number, which is essentially proportional logarithmically to the intensity that I measure. Okay. So this thing, right? This is called the logged data, right? And it's usually what is fed into image reconstruction software, right? So it gets rid of variations with respect to incident intensity and stuff like that. And so this, the log data is itself basically the integral through the linear attenuation coefficients, right? So we kind of got rid of the exponential. So when we look at it again, along this line, right, my integral would go from, if 0 is up here, it would start changing its value as I come across here to this point. At this point, just as I exit the patient, I have this intensity, right, that I'm going to measure, and it's proportional to this integral. Right? Yeah.
Log or like log natural log?
It's log, yeah. Log in the sense that since it was exponential, right, we just did log, sorry. Log base E. And so here, what's exiting the patient is this intensity. I do this, right? I measure that intensity, I perform this transformation, and I get a number here now that it is proportional to the integral through mu, right? So now I'm linear in mu. So here's an example of what raw data looks like. This is, first we'll look at the object. The object is actually a vessel we printed on a 3D printer that has an hourglass shape. So this is the resin. Inside the vessel is contrast agent. This is the cap with contrast agent inside it, so it's brighter. And then these are 2 pacing leads. We were interested in whether or not we could detect things on pacing leads when we were doing this experiment. I think I can make it rotate. So it should be, there. So it's 3D object. Z is this direction, so this is superior, inferior, and then we're rotating around, looking at it from different angles, right? From the view of the source, the X-ray source. We're just rotating around, looking at our object, right? So that's what the X-ray source sees when it rotates around. This is the raw data extracted from the scanner for that object. Okay, so this is actually ID, right? And so where you have a lot of X-ray attenuation, you see a lower ID value, right? And in the background here in the area, you see a higher ID value. And then, so as that detector is rotating around, this is what it's measuring. Okay? Now, this data is not corrected at all, right? In terms of corrected for intensity of the emitted radiation, corrected for the difference in amplification on the different detectors and things like that. This is just what came out of the scanner, right? It's raw data, pure raw data. But this gives you all, the views that you see that are sufficient to reconstruct the object. Here's, I should have made G of that thing, but I didn't have G of that thing. And in fact, to get G from an actual imaging system, you usually have to lean on the manufacturer to help you get it, because they know all of these correction factors and how to normalize to the incident beam and stuff like that. So you can look at the raw data, but you can't really get this, which is once the manufacturer has taken the raw data and done all of their corrections, they can give you back this data from which you can then make a reconstruction of the picture, right? So this, again, is after the log and also after some corrections have been made. And it's through a person, right? And you can see the spine here. This is the profile of the heart. The liver is here. Chest wall is here. And you see there's some particular angles there that are problematic. So when we look at this here, look at all the noise, right? There's uncertainty in what the values are right there. And the reason there's uncertainty there is we're looking at the patient from their right arm through to their left arm. So it's the longest travel, right, along that beam. And so the most X-ray attenuation is going to occur along that beam. In fact, it looks like the detectors are starting to run out of X-rays at that point, right? Whereas up here, it's just going through less material, or up in the air, it's going through less material, and so you see, a clean signal. So noise in X-ray is a little complicated. It actually, the higher your contrast, the higher your noise, right? Because contrast is attenuation of photons. But if you attenuate them all, you get a very low confidence estimate in how many you have, right? And so, but you can see details, and this is the data that is used to reconstruct a 3D image. Okay, so our mathematical problem is to take that data that I just showed you, this stuff, which is the G as a function of L and theta. So we click through different thetas just by looking at the movie. So we have G of L of theta, and we want to map that back to mu xy. And that's going to be our picture. Right? It's what is the mu xy at each location in the field of view. Just to be clear, this is thinking about things in 2 dimensions, right? When I go back to this data, this is in 3 dimensions. In fact, this is the z direction or the SI direction, right? This analysis is 2 dimensions, so it's one slice of that data, right? And if we come back to here and I take a slice right through there, just one slice, and then rotate that slice around, that's what we're talking about in terms of the GL theta. Okay, so in this, I have 256 GL thetas here, and we're just watching them all change at the same time. Okay. Is that clear? Everybody have that? No. Okay, I would stack a whole bunch of these together to do this. Okay, so let's look at this issue with parallel beam versus fan beam. That's been bothering you for the last 20 minutes. And it turns out that the math of doing back projection, doing the reconstruction, is all developed under the assumption that you have parallel beams of X-rays through the object. And then you click theta and you get parallel beams again. You click theta, you get parallel beams again. So what happens in a fan beam? So let's look at first of all, in a parallel beam, let's look at how we would plot these values. If I have a specific theta, let's call this 90 degrees this way. This orientation of beams is 90 degrees. And I plot along L here, my data along here. Okay, so I get these values. So I'm going to fill out this GL theta space And with that one projection, I'm filling out that line right there. And then I rotate, click to go theta equals 120. I measure my data along L, and I get that data there. Okay, so that's, I'm going to do that about 500 times and just fill in this whole plane of GL theta. Okay, that's going to be called a sinogram. So what happens if I have a fan beam? Well, if I start here and my L, or my position on the detector, is along this arc here, then what occurs is when I'm set at 90 degrees, right? So the central beam is at 90 degrees, right? These ones are lagging, right? And these ones are ahead, just in terms of angle. There's still beams through the patient. They just progressively change their angle. So instead of everybody being at 90, I'm going to start at 90 minus 30 degrees to 90 plus 30 degrees, right? And so this one here would be 90 plus 30 degrees. It would be over here, 90 minus 30 degrees here. And so that is how I'm sampling GL theta with a fan beam. With a single fan beam shot, I'm taking a diagonal sample through this function GL theta. Right. And so you can imagine I'm just going to click over an angle again and do another diagonal shot. And I'm just going to go through GL theta on these diagonals and map out the same function. It's just I have this tilted coordinate system for my samples. So you have to, in order to cover the same distance, the same distance in theta basically, and to map out the same amount of GL theta unequivocally, when we do fan beam, we need to go 180 degrees plus the fan angle. So I have to do some extra views to fill in this stuff over here. I just got to keep going, and I'll fill in this stuff. So that's fan beam geometry. And I think we just explained this. Any questions on that? Might just go through it a couple of times, explain it to yourself. It's fairly straightforward once it lands. Okay, when we reconstruct the picture, okay, and we'll look in detail about mathematical ways of doing this, we're going to wind up with an image of linear attenuation coefficients, or mu values, as a function of position in the plane. And this is historically how those values have been displayed in CT images. And historically, it's probably because they were initially limited to, 10 bits or something like that, in the early days. And so this system for displaying values has been around since the beginning. And so the CT number, or the Hounsfield unit, right, that is displayed on the screen is equivalent to the mu value of that pixel minus the mu value of water divided by water. So it's the fractional difference of that pixel from water times 1,000. And the 1,000 is just, I need to make integers so that I can encode this into an integer picture, right? So the levels are integers. I mean, you could just as well do this if you had a floating point picture, but in early days of digital imagery, you needed values sort of between minus 1,000 to 1,000. 8 bits would give you 256 levels, right? So 9 bits gives you 512, 10 bits gives you 1,000. So this, you have to know this value very accurately, right? And so this is measured every day. They put a water phantom in the scanner, they push go, they measure that value, right? And that's used that day as the calibration for the mu value. And they also measure air, right? And the scaling is set such that air is minus 1,000 and obviously water is 0. Okay. So you can get water is 0 from this. This is also set, right, to give you the full dynamic range. Right? So the maximum intensity that you're going to measure gives you the signal from air, and that's minus 1,000. So you get to know these numbers for different tissues, right? They're characteristic of different tissues. So skeletal muscle, Hounsfield unit's about 100, right? So that means fat is minus 120, bone is 750, blood with contrast agent in it, 650. Myocardium is the same as skeletal muscle, about 120. Right? So, and remember, water is 0. Okay, so 120 means it is 100 over 1,000 times more than water. Right? Just in terms, so it attenuates more than water, but not a heck of a lot more than water. Whereas 750 means it attenuates considerably more than water. Calcification is something that's seen on a lot of imagery, and calcium absorbs X-rays very well, and so you find very large Hounsfield units there, high absorption there. If we look down in the lungs, right, so we go down and look at signal down here, the lung is about minus 800, where air is minus 1,000. Right? Anything else down there? No? Not much?
Sorry, I just have a quick question. So how would you explain the lung again, like the negative sign in 4,800? You said that is less than
Yeah. Yeah. So air is set by that calibration to minus 1,000.
right, and the
Yeah.
lung then would be negative 800 with respect to air, you mean? Or like how much?
With respect to air and what the water calibration was that day. Yeah.
Oh, when you look at calcification, so it's not going to be like, if you look at a system, it would be uniformly calcified, right?
Right.
So that number is going to like decrease then, would it? Because with the X-ray hit it such that you would get some other calcification.
Yep. It depends on its shape and its size and things like that. But if your spatial resolution is sufficient, what we're talking about here is can you estimate the Hounsfield unit or the mu value, because you can map it back to an actual mu value for each position using that calibration equation. Inside that voxel, I've estimated the mu value. And in calcium, you're right, it changes a lot. It depends on the density of the calcium, sort of sometimes on the partial volume, because sometimes calcium can be very small, right? And so that'll change quite a bit.
Could you tell how much is like occluded when you look at the artery?
Yes, absolutely. One of the problems about calcium in the coronary arteries is oftentimes the calcium is quite large compared to the lumen of the artery itself, and the calcium has a very high brightness, high signal, right? And so you'll get a 1,300 Hounsfield unit, and inside the lumen of the artery you have 300, and so the broadening or the lack of spatial resolution broadens out this big signal and kind of interferes with the stuff you're trying to see. So that's for whatever reason called calcium blooming. It's just essentially lack of resolution, right? Okay, so the first way CT images were reconstructed, the way Hounsfield did it, was just basically direct inversion. So you essentially, this is a simple way of looking at it. If I have a volume and there's 4 mu values in that volume and I want to figure out what they are, I take projections this way and I get a P1 value and a P2 value, and I know from my log equation that we just wrote down that P1 is equal to mu1 plus mu2, right? So that's the integration along that line. In this case, it's very low number of pixels, right? We just have 4 total pixels, so 2 this way. And then across here, the integration gives me, I know it's mu3 plus mu4. I don't know what they are yet, but what I do know is this value and this value, right? And then if I project down this way vertically, or down the through the matrix vertically, and I get a projection P3, I know it's mu1 plus mu3, and I get a projection this way, and I know it's mu2 plus mu4. All right. So it's essentially a system of equations. Right? So you have, these are the things you know, and these are the things you don't know. So you just want to get enough equations such that you fill out the rank of the matrix when you do the inversion to be able to solve for all of the mu values. Right? And here you've got 4 equations. We have 4 unknowns. Unfortunately, these aren't independent equations, right? So we don't have a full rank matrix here. You can create P4 just by a linear combination of the other rows, and so you need to get another measurement that's independent, right? And so another way of doing that would be to get P5, which is a diagonal measurement here, and now these equations are linearly independent, and you have a full rank matrix that you can invert it. That's kind of gives you the idea of where resolution comes from, and that you need more independent projections in order to fill out this matrix, right? However, this is not commonly the way CT reconstruction is done anymore. This was the way Hounsfield did it when he had like 40 by 40 pixels or something. We've got 512 by 512 pixels, right? This becomes an enormous matrix, right? So if you look at it, it's obviously n squared by n squared is that's how many dimensions you have in this matrix. So that's a lot of equations. So it doesn't really work that well because of the instabilities and doing that kind of inversion, etc. Who knows? Maybe, deep learning down the road will get into inverting matrices and just go, oh, I know the best inversion for this, like pretty darn close, and it'll just invert it, So what's done most of the time is called back projection. And we have run out of time, so we're not going to talk about back projection now. We'll start there next lecture. However, I need to take a quick poll. We're going to do, or you wanted to do a linear systems.
Yeah, so we're planning to do 2 supplementary sessions, one on linear systems and 8-Fourier transforms, and then the second one on long-Fourier transforms. So you can both address either one, it depends on what you want to cover. So the plan is to have the first one this Friday. So just to show up hands, who might be interested in coming this session? Okay, so there's enough. This Friday at 10 work for most people? Okay, so I'll send out an email. And I think that's few enough people that are interested in my conference room, so I'll just send directions to that. And then the next one will be, go ahead.
Would it be possible to shift it to like 2:30?
Would 10:30 work for everyone? 10:30 to noon? I think some people have a noon class though, right?
I'm coming from class at 9:30 to 10:20.
Okay, so 10:30, does 10:30 to noon work then? You don't have a problem with 10:30 to noon? Okay, so it's 10:30 to, yes, you have a problem.
Yeah, so there's a little longer engineering class. 11 works straight for me. But I mean, I'm just one person now.
Well, okay, you guys can have. So we'll do 10:30 unless someone else. But you can send the email with issues, and I'll send the directions to the room. And then the next one will be offered not next Friday, but 2 Fridays.
Great.